right, y'all, we're going to talk about some specific kind of functional impairment expectations and anatomy involved when we have particular arteries impacted from a stroke, hemorrhagic, ischemic, you name it. But before we do, we got to do a quick review. So this is a vascular event. You got to know your vascular system. We split our vascular system in our central nervous system to anterior and posterior systems. Posterior looks a lot busier, but actually our anterior circulation tends to get more and more trouble in terms of frequency for strokes. But any one of these guys are fair game for any type of blockage, clot, hemorrhage, AVM, you name it. And really what's important too is not only to refamiliarize, I'm sure this picture is like straight out of your neuroanatomy nightmares, but not only kind of, okay, knowing where those arteries are, but most importantly, kind of knowing the roadmap. I care more about you knowing the roadmap. I care you knowing about what artery leads to what in general. So for example, because we're going to talk about anterior cerebral artery strokes, MCA strokes, middle cerebral arteries, PCA, a couple others, but we're not going to actually spend any time today on internal carotid artery strokes. And that's not because they happen, but because we can kind of put two and two together as we go through. You absolutely can have an ICA stroke. And I don't have a nice picture or geographical distribution that we're going to go over in a second of what the ICA, what areas of the brain the ICA covers, because it's kind of a precursor vessel, right? But the ICA feeds into the ACA and MCA, so it shouldn't be that surprising that if someone has a clot or a hemorrhage in their ICA, that those two big bad boy arteries are going to be impacted. So that's why it's important, is if you see someone who comes in with an ICA stroke, you got to be able to attach that to wanting to check out the impairments that might be associated with an ACA or MCA stroke on that side as well, okay? Okay, so then where we're going to spend the most of our attention are on these three heavy hitters in our cortex. So our cortex is supplied by three main arteries for the most part. There's a few others, but this is where we're going to spend our time. Our anterior cerebral, middle cerebral, and posterior cerebral artery, ACA, MCA, PCA. And this is their vascular distribution on our cortex in a variety of different views. So this is just looking at it from the side. This is a mid-sagittal view, and we're looking up at the bottom of our brain from down here, looking on our way up. And you know me, and I love my colors and my color codes and my visual images, because that is how I learn. So I'm just going to be throwing colors at you left and right today. But I really like this distribution because it just shows you nice and clear cut where each one of those vascular distributions start and end. And that's going to be important in a second. We cannot forget about the middle of our brain, though. The side of our brain gets a lot of attention, but really those deep brain structures, our thalamus, our basal ganglia, corpus callosum, internal capsule, all of those have such crucial roles to play in our functionality and our descending motor drive, ascending pain control, you name it, communication from one hemisphere to the other. And they have their own blood supply too, and they are supplied by different branches of these primary cerebral arteries, with the one exception of our anterior choroidal arteries. This guy down in green, that stems off of our middle cerebral artery. But by and large, these deep brain structures are coming off of these major arteries too, so we need to be able to associate those as well when we think about these type of stroke syndromes. So spend some time here. It's a really nice picture. You've got the kind of distribution on the right, and then all of the, in case you're a little rusty on your identifications for neuroanatomy, it has it on the left there for you, so you can kind of compare the two sides of the brain. So then once you kind of refamiliarize yourself with the vascular, the next part should hopefully be easy, because this hopefully is ingrained in you. If it is not, let's chat, because I'm impressed you made it this far. If that's the case, this should be hopefully pretty straightforward by now. The general roles of each lobe, right? Our brain is a map. It is a road map. It is a city map. Every millimeter has its own function. And of course, it varies a little bit person to person, and it varies when we look at left versus right side. But by and large, we can attribute some pretty specific roles and functions to each area of our brain. So make sure you really know this front, back, eyes open, eyes closed, 6 different languages before we move on. And in the same breath, your good old homunculus. Can't forget this guy. This is Old Faithful. It's such an important part here, especially because Why I put so much more emphasis on really knowing the ins and outs of the neuroanatomical distribution of function in our brain for strokes is because strokes are more focal than brain injuries. Brain injuries can kind of be all over the place. They spread out a lot more. They have a lot of different sequelae that can impact other areas of the brain. There's a lot more going on. This is a more focal injury. Now, you can have a huge focal injury, but it's still focal. So it's going to be easier and a little bit more clear cut for you to decide what you're expecting to see based on where this stroke is when you compare it to something like a brain injury. So that's kind of a nice thing about strokes and figuring out the who, what's, and where's. But you got to know the homunculus. You got to know that medially in our motor and our sensory strip in the middle of our brain, that is our lower extremity. You got to know as you move more laterally, you're making your way up to your upper extremity in your face. You got to know this stuff forward and back. So then what do we do with all of, okay, we just reviewed all this and, I'm over it. I remember this stuff. I'm good. How do I put it all together though? I'm still confused. Combine your maps. Combine your maps. Take your vascular distribution, take your lobes, take your homunculus, and slap it all together. Line them up just like I did here, and then look at them. So, okay, here's and this is literally, if you can do this, you've got 90% of the battle on what to expect with an ACA, PCA, or MCA stroke. Okay, here's my ACA. It's the middle part. It goes a strip, like a landing strip, right down for an airplane onto your brain. Right down the middle of your brain. You got your frontal lobe, your prefrontal cortex moves all the way back. And by the looks of it, it looks like it goes right kind of to where that primary sensory strip is in my parietal lobe. And that's looks where it teeters off. Okay. And it's medial. So that's probably going to tell me some clues on what to expect with this person. We've got some frontal lobe involvement. We've got some parietal lobe. We've got our motor strip. We've got our sensory strip, but it's medial in my homunculus. I'm going to go back and I'm going to figure out what that means. Okay, I'm with you. We've got our PCA. All right, let me look down. Woo, that is my entire occipital lobe. That's my vision center. This guy's going to have some visual problems, but hey, don't forget, depending on how big that is, if this whole PCA is knocked out, I've got some temporal lobe involvement. So what part of that temporal lobe, what down there is important? Where does that part of our temporal lobe play a part? Okay, we're going to figure that out. What are these deep structures? That's our corpus callosum. What might that mean if I had a bigger PCA stroke, that kind of thing. And then, oh boy, look at this MCA. If that's not a lot of yellow, I don't know what is. Your MCA, let's look at this. Okay, we've got our frontal lobe, and look right there is our Broca's area. Okay, we've got our parietal lobe. There's the lateral part of our motor strip. There's that's still our frontal lobe, sorry. Then we go to our parietal lobe, and we've got our sensory strip right there. We've got our temporal lobe. Oh, there's our Wernicke's. Holy cow, there's a lot going on, especially on that left side. I've got 3 out of our 4 lobes involved in my MCA. I could see how an MCA stroke would probably be pretty significantly impactful if someone gets that entirely blown out. That's sort of how your train of thought's going to go. But then an important thing not to forget is that there's a huge difference between our left and our right brains. Most of us have a dominant side. So everyone has a dominant side of their brain. Most of us, that dominant side is our left side of our brain. And most of us, our dominant side is, as this graphic displays, kind of our more logical, pragmatic, systematic, analytic side of our brain. Whereas our non-dominant, which is usually our right side, is kind of the more whimsical, artsy, emotional, creative side of our brain. Our left side of our brain is typically where the language centers are found. Our right side of our brain is typically where we have those perceptual zones of our brain more so. So all those perceptual deficits that we talked about, much more frequently associated with right-sided lesions than left. Not to say impossible, but that's typically what we see, and it's typically our parietal lobe. So huge differences. So when you look at the brain, they look the same. Anatomically, mirror image of one another. And a lot of the functions are still mirror images. So like our motor strip, for example, looks the exact same on the right as it does the left. Our sensory strip, left. A lot of our association areas, right, left, totally same. But kind of the overall theme and some really important key distinctions between our right and our left is something that you have to take heed to. We don't know why this is. We don't know why that significant asymmetry in terms of kind of the flare of one side versus the other exists, but there's no doubts about it. And I bet a lot of you would self-describe yourself as either a left or a right-sided, right-brained person. I'm very much a left-brained person. I'm science and math all the way. I always did well in those classes, and I always did horribly in my art classes. I can't draw a stick figure if my life depended on it. And, you know, I did so bad on my English SAT and GREs. I made up for it with my math, but I never did well on that side. So I'm definitely a left brain person. And I'm sure you can pick one. A lot of people can kind of be like, oh yeah, I'm right brained, or oh yeah, I'm left. Here's some just kind of more concrete examples of how our right and our left differ, and kind of looking at different tasks and things that we do. So with language, our language centers our ability to understand and produce languages on our dominant side, usually our left, but that doesn't mean that our right's not involved. Prosody is very much involved in our language, so the emotion that we put behind that production of speech is on our right side. Our ability to interpret the emotion and prosody of someone who's talking to us is on our right side, those kind of things. So you can kind of work your way down this chart. I really like these two charts. It's a nice way to distinguish some examples. And there are more examples than this. This is not an all-inclusive thing, just to kind of orient you a little bit. Okay. We're going to fly through this because really, hopefully you can, I don't have much to add in terms of everything that I'm already giving you on these slides. So our anterior cerebral artery, the two biggest take homes with these guys, when you look at the neuroanatomy involved, we've got frontal lobe involvement, and we have the medial strip of our parietal lobe that involves our motor strip and our sensory strip as well. The medial part of our motor and sensory strips, when we look at our homunculus, is our lower extremity. So generally speaking, ACA strokes will have more involvement in the lower extremity when compared to the upper. Not to say you won't have upper extremity impairments, it's just much less. So those are kind of the two biggest characteristics of these guys: lower extremity, frontal. So a lot of executive function, cog, attention, those kind of things. Behavioral issues are more common with ACA, CVAs because we're dealing with that frontal lobe and specifically our prefrontal cortex as well. Some minor differences between left and right, but it actually doesn't tend to differ. There's not a lot of distinguishing differences left versus right other than contralateral sides for the most part with our ACAs. This is some additional things you will see with ACAs. I also added kind of, sometimes we don't fully get why we see certain things. So if there's a question mark, that's why. But here is kind of the common things that we could see with ACAs and the structures that are involved with it. Okay. MCAs are the most common stroke. Left MCAs are the most common stroke, followed by rights. And this is where we do see a pretty significant difference when we compare right versus left in terms of additional impairments. At the basics, when we look, so this also is going to hit our motor and our sensory strips, but now we are much more lateral on that homunculus. It's the lateral part of our brain, the MCA. The ACA takes care of the middle. The MCA does all the rest in the lateral side. So the lateral side of our homunculus is going to hit our upper extremity and our face. So these guys will have much more involved upper and facial weakness as opposed to lower. Not to say that they can't have lower extremity involvement, it's just much less, okay? And I'm going to talk about the aphasia and then neglect in a second. Also important to note about our MCAs is the deep structures in which it innervates. So specifically, so off of the main branch of the MCA, before it splits into a superior and inferior division, that main stem you'll see has these little, I should have put a picture of it, a little itty bitty like spider leg like arteries that stem up right on top of it, and they go right into our internal capsule. That area of our brain, this white guy right here, and when we see white, that means descending or ascending axon. So these are tracks right here. They're coming up from here. They're moving their way down. The internal capsule is the one-way highway for our descending motor tracks, all right? And it is exclusively innervated for the most part by these little bitty, teeny, tiny, spidery-like arteries that stem off of our MCA, and they are called lenticulostriate arteries. Little itty bitty, teeny arteries in general will be much more susceptible to things like hypertension because they just can't hang. The smaller the artery, the weaker the artery wall, and when there's an increase in blood pressure, it's not going to handle it well. So chronic hypertension, unchecked hypertension can hit these guys pretty easily. They tend to hemorrhage, but you can absolutely have clots here too, but it tends to be a hemorrhage. And when you do, you knock out your internal capsule. What's really interesting about a lenticulostriate stroke, so if the rest of the MCA is fine, Just these little itty bitty guys that knock off our internal capsule. That means the only thing that's really going to get knocked out is those descending motor tracts. So what we have is a condition where we see pure hemiparesis with no other symptoms, no sensory loss, cog loss, anything else. Really interesting, just motor loss, and usually pretty significant motor loss because we're knocking out all of the tracts. Now, depending on the significance of the infarct, depending on how long it goes unchecked, or you may have additional areas of the MCA involved, it can extend and you can have additional cortical deficits. But by and large, when we think lenticular striate, we think pure hemiparesis. They are also called lacunar, LACUNAR infarcts as well. Here's another nice chart for you. You are welcome. So the biggest, but then I also have a second one here. So the biggest differences that we see left versus right does tend to be in our MCAs because we hit those parietal lobes and the frontal lobes too. And this is really the areas that we see the most distinguishing characteristics, right versus left. The left side of our brain has our language centers, and they are predominantly in our parietal and our frontal regions. Our Broca's is in our frontal region. And then our Wernicke's area, so Broca's is for speech production, Wernicke's is speech comprehension. Our Wernicke's is kind of right at the parieto-temporal junction, if you will, both of which are vascularized by the MCA. So you can have, depending on the significance of how much of the MCA is impacted from the stroke, depending on the area, you can have one type of aphasia, Broca's, one type of aphasia, Wernicke's, both, combination of the such. But we're only going to see that when we have our language centers in our dominant hemisphere, our left side involved. If someone has a right-sided MCA stroke, they will have no problems typically, unless they're one of the rare few that has their language centers on the right, but that is very rare. Their language is going to be fine, but where these guys really break down, the most notable way is this is where our perceptual zones are. This is our parietal lobe, where we can see all of those different perceptual deficits, and then most notably neglect. So neglect is very, very common with right parietal lesions, and typically is not common with left. So those are some big differences between the right and the MCA. I wanted a separate chart for them because this is where we see the most distinguishing characteristics, one side versus the other compared to the other guys. PCA, we think PCA, we think occipital lobe, we think visual loss, and that's the crux of it. That's really where the majority of this breakdown happens, most commonly in the form of homonymous hemianopsia. There can be other visual deficits too. We're going to talk about a specific syndrome when we have a bilateral occipital infarct in a minute. Depending on the size of the infarct, if you'll remember, our PCA does innervate the lower part of our temporal lobe, and that's where a lot of our memory centers are, so we can see memory deficits. We'll also notice when you look at the deeper structures of our PCA is that we do hit our corpus callosum. That's that big white highway right here. That is our connecting fibers that help our right and our left brains talk to one another, so we can have a breakdown there as well. Here's a nice kind of another table for you. You can read through. And then I also put this in right here. This is actually out of Lundy Ekman, the neuroscience book. Just a nice another chart for you should you want another resource or just a different way to look at the information. This kind of summarizes it up pretty well too. Last but certainly not least, before we talk about some specific syndromes, we cannot forget about our cerebellum. So we can have brainstem strokes as well too. We're going to talk about some specific ones when we talk about syndromes. We're still going to keep it pretty basic with cerebellar. And just like the cortex, where we see deficits is based off of where in the cerebellum is damage from the stroke. There's 3 arteries that supply our cerebellum. You have your superior cerebellar artery, or our SCA. You have our pica, our posterior inferior cerebellar artery, and you have your anterior inferior cerebellar artery. And depending on which one of those get impacted from the stroke will dictate what areas are involved. Cool thing about the cerebellum, if you'll remember, it has its own homunculus. I have it down there in the bottom right, which also can kind of help you start narrowing down. The more midline you are in the cerebellum, your spinocerebellar region, for example, is going to impact your trunk more. As you start to work your way laterally, as that cerebellum kind of comes around and you're in your cerebrocerebellum region, it's going to affect your limbs more. And so I have kind of some of the distinguishing factors there. But general cerebellar features that you tend to see across the board regardless: nausea, vomiting, nystagmus, a lot of visual breakdown, vertigo. They can have a lot of dysarthria problems. Our cerebellum also has a huge role in controlling our tone. And interestingly, a lot of times you're going to see hypotonia with these folks, but you can see either hyper or hypotonia. So that's kind of an exception to the norm of when I went on my whole tangent about how we typically see increase the tone and not quite so much decrease. This is kind of the one exception to the rule. Incoordination, ataxia, and headaches are really common for these folks too. They tend to be posterior headaches though, not up front. All right, we're going to pause here. We'll talk about some syndromes, and then we'll wrap it up with prognosis, and that's all I got for you. Okay, see you then.